Right now, companies like Meta, Google, and Microsoft are spending tens of billions of dollars to acquire hundreds of thousands of new GPUs. A GPU, or graphics processing unit, is the specialized chip required to train and run modern artificial intelligence models. To house this hardware, these companies are building sprawling facilities that demand over 100 megawatts of electricity. A single modern AI data center now consumes as much power as an entire small city. Inside these buildings, thousands of individual chips must constantly talk to one another to train complex AI models, moving mountains of data back and forth 24 hours a day. Physical power draw and the resulting heat have overtaken software as the primary bottlenecks for AI scaling. Today, these chips connect and send electrical signals to one another through traditional copper cables. The current industry standard for these connections is roughly 800 gigabits per second. Training the next generation of models requires doubling that speed to 1.6 terabits per second. At that velocity, the power consumption and heat generated by copper cables scale exponentially. Because of this extreme heat, the electrical signal itself physically degrades. Even over a distance of a few inches, the data breaks apart before it can reach the next chip. This signal failure is a fundamental law of physics. To continue scaling, the hardware industry is being forced to abandon copper wiring entirely. The industry is pivoting to silicon photonics. It's a method of using light, rather than electrical currents, to transfer data between computer chips. Instead of pushing electrons through metal wire, engineers are now pushing photons through tiny glass pathways etched directly into the silicon. At the individual connection level, these optical links are 3 times more power efficient than their copper equivalents. Applying this efficiency to 50,000 separate links removes megawatts of demand from the local grid and dictates the operating margins of the entire facility. By solving the heat and power crisis, silicon photonics has transitioned from a lab experiment to a mandatory piece of infrastructure. The financial markets are reacting to this shift now. In just a few weeks, NVIDIA committed $4 billion to optical component companies, while Marvell closed a $3.25 billion acquisition of a photonics startup. This capital is flowing through 3 distinct layers. At the base layer, NVIDIA is integrating optical connections directly into its Vera Rubin supercomputer platform. Alongside them, Broadcom is designing custom AI processors for hyperscalers and currently supplies 80% of the Ethernet switch chips that route data across these centers. Intel also occupies the base layer, leveraging a 25-year head start to operate the only large-scale optics-based manufacturing foundry available to outside customers. Below the designers is the middle layer. TSMC, the world's largest contract chip manufacturer, is currently building dedicated production lines specifically for photonic components. They are joined by fabrication companies like Tower Semiconductor, Global Foundries, and Fabrinet, all expanding factory capacity to physically assemble these optical modules. At the top layer, companies like Coherent and Lumentum design the specialized microscopic lasers required to generate the light. The synchronized move by designers, foundries, and laser manufacturers commits the global hardware ecosystem to an optical roadmap for the next decade. This chart shows the projected expansion of the silicon photonics market. It tracks a trajectory from a $3 billion industry today to an estimated $30 billion by 2034. While the public focuses on which company designs the fastest individual processor, the actual physical constraints of AI have moved to data transfer speeds and power grid limitations. The long-term winners of this build-out are the companies providing the raw materials, fabrication lines, and optical lasers required to solve the power crisis. The ceiling for artificial intelligence is now set by our physical ability to wire these systems with light.